The topic of this video is payout annuities. A payout annuity is actually best represented, I think, by the diagrams that I have drawn here. So a payout annuity only exists if first you make investments. If you plant those seeds in an annuity so that your money grows, there's the money tree there in the center, and then after that money has grown and that tree has grown, then you can start harvesting that money. The only way, again, that you have money to pay out of your annuity is if you have actually planted the seeds, if you have made those original deposits throughout your working years that lead you to retirement, and then you get to start reaping the benefits of the money that you set aside. The payout annuity formula is seen there on the screen. P is the principal. This is the starting amount that you have in your annuity. So you have set up a retirement account, and when you retire and you need to start then taking the money out of your retirement account, that is the principal, the amount you have before you begin withdrawing. Similarly, if you would have a college savings account, if you have invested for years in a college savings account and at the end you have, say, $50,000, that $50,000 becomes the principal once you start taking the money out of that account. W is the regular withdrawal amount. So that's how much you're going to pull out of the account on some sort of a regular basis. Now, when it comes to retirement savings, that might mean it's a monthly amount that you take out so you can pay your bills, get your food, maybe go on vacation. For a college savings account, you might only be withdrawing money, say, twice a year at the start of each semester as you pay your tuition. R, as in all of our other formulas, is the interest rate as a decimal. N is how many times you're withdrawing money each year. So very similar to our annuity, how many times you're depositing. But again, this is the withdrawal version. And T is your time in years. You will use this formula when you are making regular withdrawals from an account. So you're going to do this on, again, a regular basis. Okay, you're making regular withdrawals. So let's take a look at our first example. Bella wants to be able to withdraw $12,000 every quarter from her retirement account for 20 years. How much money does she need in her account when she retires if her account earns 5.5% interest? And then how much interest will Bella earn on her account? So again, going back to our formula. Oops, sorry. That's a P, not an A. All right, so principal is the withdrawal amount times 1 minus 1 plus R over N to the negative NT power divided by R over N. So the withdrawal amount is the $12,000. The interest rate, 5.5%. She wants to take out this money every quarter, so N is 4. And she wants to do this for 20 years. And then we have our R over N again. And do note that the exponent is negative. That is a negative NT power. So for calculator purposes, so that you don't need another set of parentheses, again, I'm going to recommend that we go ahead and multiply that together and get an exponent of negative 80, and we'll just enter it that way into the calculator. And I'm going to use Desmos.com in order to do this calculation. When you put all of that in there, all the parentheses in place, the exponent in place, etc., you will find out that the total amount she needs to have in this account is $580,036.41. Okay, now notice that that is not simply 12,000 times 4 withdrawals a year for 20 years. That is a different number. And that's actually what we're going to use or look at when it comes to how much of The money is interest. And this is the part that I know a lot of students will kind of forget about, okay? This money, this $580,000, when you take out, or when Bella takes out the first $12,000, she's leaving the rest of that money in the account. And that money continues to earn interest. Okay, so it's not like you just get to take this amount. She's got $580,000, divide it by 12,000 and figure out how long it's going to last. That would be the equivalent of taking that money and burying it in a box in your backyard. We don't want that. We want it to continue to grow interest. So the interest in this case is going to be the total that she withdraws minus the principal, the starting amount, because again, she's going to be able to withdraw more money than what it seems like she has in her account because interest continues to accumulate. So if she takes out $12,000 every quarter for 20 years, and then we subtract the principal, I'm not going to write that amount in right now. I'll write it in this next step. When you multiply this together, you find out that she is able to withdraw $960,000, even though her account contained $580,036.41. Again, she's able to withdraw way more money than what she had in there because the interest continues to accumulate as she is withdrawing that money over time. So doing that subtraction, we find that while she was withdrawing that money and letting the rest of it sit there, she continued to earn $379,963.59 in interest. On this slide, you will see the calculation that was put into Desmos to get the principal amount, how much she needed when she retired. And so again, just for reference, if you did not get to the same answer of $580,036.41, please check that you have entered it in the exact same way that I have it here on this screen. All right, moving to the next example. When Tom retires at age 65, he will have $750,000 in his retirement account. He wants to withdraw money every month until he reaches 90 years old. How much can he withdraw every month? And then, similar to the last question, we're also going to figure out how much interest Tom will earn. And we're going to make the assumption that his account earns 6% interest. So now when we look at our formula for a payout annuity, now we know the principal. We have this starting amount. That is how much is in his account when he retires. What we don't know is how much he can withdraw on a monthly basis. We know he's earning 6% interest and he wants to withdraw money every month, so N is 12. And the other thing that we can figure out is the time. Now, he is retiring at 65, and he wants to continue to withdraw money every month until he's 90 years old. So when it comes to the time is 90, sorry, not minus 25, minus 65, which is 25 years. So he wants to continue to make these withdrawals for 25 years. Now, as we go through this, again, keep in mind that this quantity right here is being multiplied by W. So we need to figure out that number times W, the withdrawal amount, will equal $750,000. So we're not going to do any rounding for that step there, for that intermediate calculation. But I'm not going to write out all of the decimal digits either. So you get 155.2 and a whole bunch of other digits that come after that. And in order to solve for W, we need to divide both sides of this equation by that 155.2 and all of the other digits that come after it. And once we do that, then we can round our answer And we will figure out or calculate that Tom can withdraw $4,832.26 every month for those 25 years. Now, how much interest is he going to earn? So again, just as a reminder, if you are to multiply that amount, that $4,832.26 by 12, because it's a monthly withdrawal, and then times the 25 years that he's going to be pulling that money out, that number is going to be much larger than $750,000, because that money, after he pulls out a little bit, the rest of it continues to grow and earn interest. So whenever we multiply out his monthly withdrawal times the 12 and the 25, we will find that he has then been able to withdraw $1,449,678. And when we subtract the principal, we can determine that he earned $699,678 in interest. So notice that he earned almost as much in interest as he had saved up originally. That is the power of saving for retirement. Not only do you earn interest while you're working, but then you continue to earn interest after you have retired. And once again, on this screen, you can see the work that was typed in. So again, I took the negative 12 times 25 and got the power of negative 300. Remember, the W would have been here in front of this expression, and that equaled 750,000. So after we do that calculation and get the 155.2 with a whole bunch of other decimals, then you need to divide 750,000 by that entire number. Again, don't do any rounding until you get to the very final answer. And so here's where that $4,832.26 came from.